Knowing how to integrate on rectangles, we now turn our attention to non-rectangles, which generally could be any shape. That being said, our goal will be to write the boundaries of our domain in terms of functions, and you'll see why that's true in a second. If we look at this diagram, we can confidently say that x must always lie between a and b, but we can't really write y in the same way. The y values are changing depending on where we are in the domain. So what we're going to do is describe how the y values change as a function of our x value. So let's start by picking a random value for x between a and b, and I'll highlight the corresponding y values above that x in the figure. Note that the smallest y value corresponds to f of x, while the largest y value is g of x. This means that we can write omega as the set of all pairs x, y, such that x is between a and b, and for any given value of x, the y values there go between f of x and g of x. If we can write omega in this form, then we can compute our integral using iterated integrals in a way that's very similar to what we did with rectangles, where notably the bounds of the y integral are now functions rather than numbers. And this integral still makes sense. If you think about what's happening in this inner integral, you'll notice that once we integrate, we plug in functions of x, and this causes all of the y's to disappear. This same sort of thing happens when we compute integrals in higher dimensions as well, but we're going to leave that to a different video. To show this at work, let's let omega be the region in R2 bounded by y equals x squared and y equals 4x. Let's compute the integral of the function x squared plus y on the set omega. With these sorts of questions, you should always start with a sketch of the region. We end up getting a region in the first quadrant, which looks like this. Now we need to figure out where these curves meet, so we'll set them to be equal and solve the corresponding equation for x. This gives us values of 0 and 4. The y values may be useful as well, and we can use either curve to get them, for which we find that y is equal to 0 and y is equal to 16. I'll add that to our sketch. Writing omega in our special form, we get that x then goes between 0 and 4. And to figure out what y does, I choose a random x and I take a walk in the positive y direction. The curve I see when I enter omega is the bottom curve, while the curve I see when I leave is the top curve. I see x squared on my way in and 4x leaving, so this is the order of my bounds. In this form, we can now write out our iterated integral as follows. We're integrating with respect to y, so remember, we're going to treat x as a constant, and sub in y equals 4x and y equals x squared into our integral exactly as if they were numbers. The remaining integral depends only on x, and we won't go into any detail solving it, but we get a value of 1792/15. A good question asked here is whether or not we could have done this in the other direction. To which the answer is definitely yes. Let me bring down that sketch we had above. This time, we want to try our hand at writing omega in terms of y first and x second. We can see from the picture that y lies between 0 and 16. Now we want to determine the x values depending on a given choice of y. So let's choose a random number y and take a walk in the positive x direction. This time, I hit y equals 4x upon entering omega, but importantly, I need to write this as a function of y. So solving y equals 4x for x gives us y over 4. Now we leave on the curve y equals x squared, but solving this for x gives us the square root of y. And it's important to remember that in this case, we have to write our curves as functions of y in order to get out their x values. Writing out the iterated integral in this form, our bounds change, as does the order of integration. And you can check that you get exactly the same answer as above. Now sometimes it's easier to write your domain in one way over the other, And in some cases, it's only possible to do the integral if you write it in one particular way. But in terms of practicing, it's probably a good idea to try both ways and see if you can make it work.